Thank you very much. Hello, everyone. My name is Changhao Wang. I'm a fourth-year PhD student at UC Berkeley. I'm working with Professor Masayoshi Tomizuka. It is really my honor today to present our recent work on online gain optimization for variable impedance control. As we all know, impedance control is very effective for many contact-rich manipulation tasks. It can regulate robot movements by mimicking a mass spring damping system. So as a result, the robot behavior can be determined by those mass and spring damping those values. And variable impedance control, in addition, provides the flexibility to adjust those impedance gains according to different scenarios. But for practical use, the challenges are how to tune those impedance gains to get the best performance, and even more challenging, how to adjust those impedance gains online for time-varying environments and task objectives. There are already lots of previous works to try to deal with this problem. Adaptive control methods can adjust those impedance gains according to a predefined adaptive law. However, the problem still exists. For adaptive control, you still need to pre-tune initial impedance gain. And moreover, the adaptive control will also introduce more hyperparameters to the overall system, which makes the tuning even more challenging. And also, there are lots of works on reinforcement learning to offline learn the policy according to a reward function. However, as a common problem for machine learning-based method, it is data hungry and not efficient to train. Moreover, there exists a sim-to-real gap when we implement the policy on the real robot. The optimization is also a very powerful way to find the optimal impedance gain. However, most of the existing methods highly relies on black box optimization to solve an overly complicated problem. The reason is that the relation between the impedance gain and the robot future behavior is missing. So we can now use those information to use gradient-based method to efficiently update the impedance gain online. So most of the methods here are all offline. And so what we want to do is to propose a method that can obtain the optimal impedance gain online without any human tuning and can be used in different scenarios. So in order to achieve that, the first thing we do is to explicitly construct a dynamics between the impedance gains and the robot state. If we have the relation like this, we know how we change the impedance gains can achieve the robot desired behavior. And based on that, we propose an efficient online gain optimization framework to achieve those tasks. And we also consider how to avoid unwanted collisions with impedance control by just tuning those impedance gains. So first, let's take a look at our structure. As we just talked about, there are two problems we want to address: obtain the optimal impedance gains in real time without any human tuning, and also establish safety constraints by just adjusting those impedance gains. Since in practice, safety always has the highest priority. So we break the optimization into two levels. A high frequency gain optimization for safety. It will be achieved over hundreds of hertz just to make sure the robot do not collide with a workpiece that we do not want it to collide. And there's also a low frequency gain optimization just to trying to find the optimal impedance gain that we want for a specific task. And it will be done in every 2 or 3 seconds. So the overall structure is something like this. The optimizer will take in the robot current state and a series of external force data into account and solve an optimization problem. And the solved impedance gains will send to an impedance controller to control the robot and regulate future robot behaviors. So let's take a look at our details of how we achieve this. So as we said, what we want is to have a real-time optimization method to obtain the optimal impedance gains online. So in order to achieve that, it is desirable to have a relation between the robot behavior and your impedance gains. So here, let's take a look at how we achieve that. So for preliminaries, Cartesian space impedance control can be written in the form of equation 1, where M, KD, and KP are those impedance matrices. And we assume that those matrices are diagonal and positive definite. So we can left multiply M inverse and obtain equation 2. So here, M inverse KD, we call it KD prime, and M inverse KP as KP prime, and M inverse, we call it the transformed impedance gain values. And those are the values that we're trying to solve. So just by collecting terms of equation 2, actually we can formulate the relation between the robot behavior and impedance gains, where the robot behavior can be represented by the robot state error and the position error and its velocity error. And we can formulate a control outline form where U is the transformed impedance gain matrices. And it is very interesting that by just doing this reformulation, it is a dynamics that on the right hand is the impedance gain, on the left hand is the robot behavior. And the only thing that we do not know is the F, is the external force, but actually we can measure it from the online phase through the FT sensor. So if we have the relation here, we can construct a proper objective function or constraints in order to regulate our future robot behavior. And that's the key for our proposed method. So for the objective function, our goal is to let the robot to behave smooth and stable for contact-rich manipulation tasks, while at the same time, we do not want the robot to oscillate at the surface. And actually, ITAE is a very famous method for tuning PID controllers, which is to minimize the integral of time-weighted absolute error. And for contact-rich manipulation tasks, instead of consider a zero tracking error, people more care about the velocity, the velocity profile that we want the robot to behave smooth. So inspired from ITAE, we propose a new objective function called FITAVE, which is to minimize a finite time integral of time-weighted absolute velocity. So we try to regulate the velocity error in order to make the robot behave smooth. To make a simple example to illustrate the intuition of this FITAVE objective function, here, imagine a robot is at position 2, and it will contact with the surface at position 1, which is modeled by a spring. And the robot is controlled by an impedance controller. And we try to tune those impedance gains in order to make the contact very smooth. And so on the bottom right shows the position profile for different methods, for different tuned parameters, to different tuned impedance gains. And as you can see, for a manually tuned impedance gain, the robot can achieve, there's several oscillations, but it can finally achieve very good performance. And for ITAE, it gradually begins to not oscillate, but still the oscillation is noticeable. But for the proposed FITAVE objective, using that, we can in real time obtain the optimal impedance gain that lets the robot do not behave really smooth and prevent the oscillation behaviors. And so we can also test it on our real robot. So on the left, we first show if we want the robot from a high position to contact with the surface with a pre-tuned impedance gain. Those impedance gains are tuned on a foam board and directly utilized on this plastic board. So, but directly using this impedance gain, the robot will definitely oscillate a lot and cannot stable itself. And we also try an adaptive controller proposed by another paper that the initial impedance gain is still the same as the constant gain baseline. And with the adaptive law, the robot is able to stabilize itself, but still with minor oscillation. And in the end, we also show our proposed method, still the same task. The robot begin with a high position and contact with the surface. And for the proposed method, we random initialize the robot with the impedance gain. So as you can expect it will hardly contact with the surface and result in loss of oscillation. But after our method kick in, we directly measure the external force and use the proposed FITAVE objective function to optimize the impedance gain, the robot will behave smooth immediately. And you can see the video again. The robot will contact the surface hardly, but suddenly stops after the optimization updates. And using this impedance gain, it can also robust to human disturbance. And everything is achieved in online phase. Similar things will happen for different scenarios. For example, in a metal board, the characteristic is different, but similar things will happen. A constant gain may not work. Adaptive control law works in some extent, but for the proposed method with a random initialization, the impedance gain, but after our proposed method, it can immediately find the optimal impedance gain and robust to disturbance. Also, we tested on more different board. For example, this wood board, but the things are very similar. So it demonstrates the effectiveness of the FITAVE objective function. It can be achieved online and to find the optimal impedance gains for different scenarios. So that's the proposed objective function. And then let's talk about how we formulate the collision avoidance constraint. So actually for many contact-rich manipulation tasks, the robots are quite close with the workpiece. And sometimes we do not want the robot to move out of a safety zone. But this research actually is quite missing for variable impedance control. And we want to address this by formulating a constraint in order to make the robot suddenly be aware of the safety, and by changing the impedance gains, it can avoid the collision with some unwanted obstacles. So for the preliminary, the first equation actually shows a sufficient condition for example, if we have a constraint h of x that is greater than 0, a sufficient condition actually to consider this is by taking the derivative. And alpha here can be selected as a positive value. And so for collision avoidance constraint, so collision avoidance is only related with the robot position or position error. So we call it HP, which is the constraints on the position, and it's only related with the robot position or position error E. So we can apply the above relation, take the derivative for the safety constraint. But finally, we find after taking one step of derivative, the control input U, which are the impedance gains, do not show up. The reason is that for this system and this constraint, the relative degree is greater than 1. So we just by taking one step derivative is not enough to find the collision constraint. So we just do one more step of derivative. H prime of x is this equation, and then we take one more derivative and find the terminal collision constraint. And as you can see, by ensuring this constraint is greater than 0, it is sufficient to ensure that the robot stays in the safe set. And U shows up here. And actually, even though this is a very complicated function, but actually it's a linear constraint over U, because every other things can be directly measured, or have closed form solutions. And when we implement this in online, it is just a linear constraint. So it is very easy to solve. So let's take a look on the experiments. For a constant gain impedance control, we do not want the robot to collide with those obstacles. But of course, a constant impedance gains are not able to achieve that. If human directly drag the robot towards those obstacles, the robot will definitely collide with obstacles. But for the proposed constraints, when the human drags the robot towards the obstacle, the controller suddenly be aware of the danger and changing those impedance gains when it is necessary. So the robot will stay in this safe zone and not exceed. So that's for the constraint. Here we show off the combined overall proposed method. there are two levels of optimization: low frequency optimization for obtaining the optimal impedance gains for different scenarios. We want to do it in online and without any human tuning. The optimization we solve is to minimize the proposed FITAVE objective. The thing that we do is to collect the first sensor data for every t seconds and use those first sensor data to formulate this FITAVE objective. And we use the standard SQP solver to update this objective function, and we can obtain the optimal impedance gain for every t seconds. And while at the same time, we want the robot to stay safe in the safety zone. So the objective is to avoid all the collisions. The procedure is according to the constraints. We first construct the safety control set, and then solve this optimization. The objective is selected to minimize the change of impedance gain, because we believe the U star is a very good impedance gain, and we want to keep that unless the robot will collide with some obstacles. So we only change those impedance gains when necessary. And so actually we also demonstrate an application that the robot to wipe a surface using the proposed method. Still the same, the robot initializes with the random initial gain, and it will contact hardly with the obstacle, with the surface. But with our proposed method, it can suddenly immediately change those impedance gains, and it all changed online, and it's very robust to human disturbance. So for conclusion, we propose an efficient online gain optimization algorithm for impedance control or variable impedance control. We also consider the safety constraints during the manipulation task. And we conduct a series of contact-rich tasks for validation. In the future works, we try to apply this on more challenging scenarios, such as polishing and grinding, which we think it is very important for the usage of those applications. So that's all for our presentation. Thank you very much for listening.